All right, let's go over the questions on the first test. So several parts here to start with part one. So all multiple choice in this first part. First thing you're being asked about is to find this limit from as x approaches 5 from above or from the right. So if we look at this graph, we only care about what's happening on this last, piecewise segment of it. So what is this function doing as I approach from the right? It's approaching a y value of -2. So this limit is equal to -2. Next, we're asked about now a standard limit, a two-sided limit. What does this function approach as x approaches 1? So as x approaches 1, what y value do I approach? So the two-sided limits, we have to look from the left and the right. We can look at them one at a time, though, and see if they agree. So what's happening as we approach from the left? So we're approaching this open circle here. So let's make some notes. The limit as x approaches 1 from the left of f of x, that's approaching that open dot, which is at a y value of -2. Now, what about when x approaches 1 from the right? So it looks like it's approaching the same value. So the limit as x approaches 1 from the right of f of x is also -2, which means this limit has to be -2. One thing I want to point out is that it's irrelevant. So at no point have I talked about what the function, like what f of 1 is. Remember that for a limit, it's irrelevant we only care about what's happening near x equals 1, not what's happening at x equals 1. So we don't really need to consider what the definition of the function is where x equals 1. All right, question 3. We want to use this table to find this limit as x approaches 1. So where is x equals 1? So basically it's going to happen in the gap between x equals 0 and x equals 2. You might be tempted to say that the limit is equal to 1, but we don't really know what's going on near x equals 1. We know what's happening at x equals 0 and x equals 2, but those are not near. So basically, we can't say anything. And to kind of illustrate this point, let's do this. So we know that when x equals 0, y is equal to 1. When x equals 2, y is equal to 1. It's conceivable, probably very easily conceivable, that these 2 points are joined by a horizontal line. But maybe they're joined by this, or this, or this. So we have really no way of knowing what's happening around x equals 1. So in this case, we can't even say if the limit exists. In this case, we really have no information. We don't have enough information to make any determination. Next, question 4. So given this, we want to find this limit. So it's tempting to plug in 0 for x, and you might even try to do that and realize that this just does not work. But that doesn't mean the limit doesn't exist. In fact, if we look at the limit of this function as x approaches 0, let's take the expression we're given and do some simplification. So every term in the numerator has an x in common. So I'm going to factor out an x. If I factor out an x, I get x squared minus 2x plus 3 all over x. So after I factor out that x, I can cancel out the x in the denominator. So this limit is equal to this limit as x approaches 0 of x squared minus 2x plus 3. So even though we could not directly substitute before, now we can. What happens when I substitute 0 for x in this expression here? I get 0 squared minus 2 times 0 plus 3. All told, I get a limit of 3. Moving on, how about this here? So most of the limits we look at, we care about what happens as x approaches some real number. Now we want to know what happens as x approaches negative infinity. So as x gets arbitrarily small, arbitrarily negative. So let me rewrite the limit we're looking at. The limit as x goes to negative infinity of 2x squared minus 9 over x squared plus x minus 3. I'm going to do some rewrites here. I'm going to basically divide both numerator and denominator by x squared, or multiply by 1 over x squared. What does that do for me? 2x squared over x squared is 2. 9 divided by x squared is just 9 over x squared. And then the denominator becomes what? 1 plus 1 over x minus 3 over x squared. So now what I've done, if we look back to our original expression, if I plug in, if I just think about what happens as x goes toward negative infinity, basically the numerator is going to go to infinity and the denominator is going to go to infinity. It's hard to think about what's going to happen there if we leave it in that form. But now, what's going to happen to these, basically any of these terms that have a variable in them as x goes to negative infinity? Well, now the variable is in the denominator, and all the numerators are constants. So all of these terms are going to go to 0. So I get 2 minus 0 over 1 plus 0 minus 0. I get a limit of 2. So, and a shortcut that I've seen a lot of you making, and basically this is the reason why you can make that shortcut, because if we're looking at what happens as x goes to infinity or negative infinity, it really comes down to what the leading or what the leading terms are, and how their degrees compare. In this case, the degree of the numerator and denominator is both 2. So the ratio of those coefficients is going to dictate what that limit is. All right, moving on to 6. So we want to find the limit as x approaches 2 of this function, this piecewise function that has 3 different definitions. So one thing I want to make really clear, and that's one of the things this question was designed to assess, is when you're talking about a limit, we don't care what's happening at this base point. I don't care what's happening at x equals 2, only nearby. So because of that, I'm going to scratch this out because this information is completely irrelevant. I don't care if x is defined at 2. I don't care what value it has. If I want to think about this limit, all I really care about is what's happening near 2. And since it's defined differently above and below, let's look at the one-sided limits here. So if we look at 2 from the as x approaches 2 from the left, so which one of these definitions of the function do I care about? That's going to come from x being less than 2. So the limit as x approaches 2 from the left of g is going to be equal to 3 times 2 minus 7. So that comes out to be -1. What about as x approaches 2 from above or from the right? Well, that's going to come from this top definition. So that's going to come from 2 minus 3. That's equal to -1. So the one-sided limits both exist. They both agree. So that means that this limit must take on that value. This limit's equal to -1. I'll go ahead and undo this scribbling here and note that this function is not, so g of 2 is -5. But all we're asking about is the limit. We don't care about, basically I could make this -15 and it would not alter my answer in any way. We only care about what's happening near the base point, not at the base point. And finally, question 7, find f prime of x if I'm looking at this limit. So what is this limit? So what's going to make this really easy for you is if we compare this limit with the limit definition of the derivative, f of x plus h minus f of x all over h. If we look at the similarities between this generic thing I just wrote down and this specific thing that the test is asking you about, What we can really do here is, you know, tease out what f of x is. F of x equals 3x squared minus 5x. And, you did not have this in your arsenal before about the time you took this test, but now you do. You can use the power rule to take derivatives like this. Again, this is not something that was available to you at this time. But let's at least kind of give ourselves a finish line. We know from the power rule this derivative is equal to 6x minus 5. So kind of already know the answer, but let's make sure that we can do the algebra and get the same result using the limit definition. So the first thing I'm going to do is expand all the brackets. So what is x plus h squared? That's going to be 3 times x squared plus 2xh plus h squared minus 5x minus 5h minus 3x squared minus negative 5x plus 5x all over h. We got one more set of brackets to expand. The limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 3x squared plus 5x all over h. Okay, so hopefully by now you've noticed that a lot of these things annihilate each other. 3x squared gets canceled out by negative 3x squared. Negative 5x gets canceled out by 5x, and that should be it. So if you'll notice now, there are 3 terms remaining, all of which have an h in common. So I will factor that out. The limit as h approaches 0 of h times the quantity of 6x plus 3h minus 5 all over h. Now I can cancel out these h's. And now what happens? So at no other step in this process could I have substituted 0 for h because I would have divided by 0. But now I can. Now I get, if I plug in 0 for h, I get 6x plus 3 times 0 minus 5. That's equal to 6x minus 5, just like we expected. And okay, I don't think this question was actually on the test. I'm not sure why I copied it down. So let's keep on going to part 2. All right, so we have this function here that describes a boulder being pushed off a cliff. T stands for the time since pushing the boulder in seconds. H stands for the height above the ground of the boulder in feet. And we have a table that gives us a few height values for time. So I want the average velocity of the rock from the time it was pushed off to the time it landed. So the average velocity, that's going to come from, basically that is mathematically no different from taking a slope calculation. So I really just want to know what is the total distance covered. So the average velocity, that's going to come from total displacement over total time. So what was the total displacement? Well, the way I'm going to get that is by my final height. So h of 4.33 seconds minus my initial height, h of 0, divided by the separation in time. So what is h of 4.33? That's 0. It hits the ground then. Minus the initial height, which is 300, over 4.33. So what is negative 300 divided by 4.33? Let's see. Okay, I am getting a final value of negative 69.3. And what units make sense here? Feet per second. All right, moving on. All right, now we're being asked about not the average velocity, but the instantaneous velocity. So how do we find instantaneous velocity? And also we're being asked to approximate it. And I think there are multiple choices here. But really, the best approximation is going to come from, think about how we bridge the gap between average rate of change and the instantaneous rate of change. Average rate of change, you have some interval, some separation in your independent variable, in this case, time. You'll have some time span. If we want to approximate the instantaneous velocity as closely as possible, we want to make that time span as small as we can. And I think there's a choice here that basically makes your time interval, 100th of a second. So 4.32 is less than or equal to t, which is less than or equal to 4.33. So if that's the very small time interval I want to deal with, then my approximation for instantaneous velocity is going to be, structurally the same as the way I did here. Change in height divided by change in time, except now those changes are going to be as small as I can make them, because I'm only going to allow for a very short amount of time, in this case, 100th of a second. And I think there was one of the multiple choices looked exactly like this. You could even make better estimates if you made the interval even smaller. All right, if this graph is f of x, what's a possible graph for f prime? So this is, a very good question for kind of getting you to think about how a function and its derivative are related. And they're related in a lot of ways. And a lot of those can kind of be assessed by whether or not you can construct a graph of one, given the graph of a function, can you construct the graph of the derivative? There are lots of ways to approach this. The way that I prefer to start is by identifying those places on the graph of the function where I know the derivative is going to be 0. So that's going to be the place where tangent lines are horizontal. So that's going to happen at maxima and minima. So where about are those points? I'm trying to keep the same scale here. I don't know, let's say 2 and -2. So this is my graph of f prime of x. This is the graph of f of x. So I know at -2 and 2, I'm going to have zeros. Okay, so now what's going to happen between those zeros? So between this minimum and this maximum, what is the derivative doing? Everywhere in here, if I were to draw a tangent line, it would be a positively sloped tangent line because my function is increasing. So that means that on my derivative, this function needs to be positive. So, and these two ideas are equivalent. If a function is increasing, its derivative is positive. So far, I think I've dealt with the fact that I have 2 points where I know my derivative is going to be 0, and I know what's happening in between them. So finally, let's talk about what happens on, to the left of that minimum. Let's do that first. To the left of that minimum, what do my tangent lines look like? They're going to be negative everywhere. So that tells me that this function is going to be negative. What about what happens to the right of this maximum? Same thing. I believe all these tangent lines are going to be negative. So I believe I have a graph that looks like this. So it looks like a concave down parabola that opens downward. And I believe there's one of the graphs that looks like this, that has basically, might not look exactly the same, but it's going to be parabolic. It's going to have zeros at these 2 points. All right, so moving on to 4. So now we're kind of going the opposite direction. Same graph, but now we're telling you this. This graph is the derivative. So this is f prime of x. Now we're trying to construct a graph going the opposite way. I give you a graph that describes the rates of change. What is the graph of, what would the original look like? I still like to do the same thing. Let's start with where the derivative equals 0. And what does that mean about my function? So my derivative equals 0 at three distinct places, right? At, I don't know, let's call these -3, 0, and 3. I feel good about 0. I'm kind of arbitrarily picking 3 and -3 as the values where this happens. So if my derivative is 0, what does that mean about what happens? And what does that mean about the function? So let's go back and kind of talk about this idea. So where is the derivative 0 at this point and at this point? What's happening on the function f at those corresponding points? Well, that's where I have horizontal tangent lines. So we can kind of incorporate that idea here. It's a little trickier because I know I'm going to have a horizontal tangent line at, I'll draw some vertical dashed lines here. I know I'm going to have vertical tangents at the y-axis at x equals -3 and x equals +3, but I don't know how low or high those are. So let's do this. And again, I am purposely not showing the multiple choices here, but let's say this. Let's say that f of 0 is 0. So this graph I'm saying goes to the origin. There might be a multiple, basically, let's cross that bridge when we come to it. So at x equals 0, I know I'm going to have a horizontal tangent. You know what? I'm going to change my mind here. Bear with me. I'm going to say that f of 0 equals 1, just so I can show you what I'm trying to illustrate. If f of 0 equals 1, then not only do I know that my graph passes through this point, but I also know that it has a horizontal tangent line here. So it's going to be a minimum or a maximum. And I think we can even say which one it is for sure. But let's keep on digging. I also know I'm going to have a horizontal tangent line at 3, which is where I have this right-hand dashed line. So let's talk about what happens in between there. F prime here is positive everywhere between 0 and 3. So what does that mean about f? If f prime is positive, then what does that mean about f? If a derivative is positive, that means that f is increasing, which means that if I were to draw this graph, I believe it would have to do this. So it has to increase for a bit. Let's try again. It has to increase for a bit, and then it has to come back to another horizontal tangent line. So one more time. I have a horizontal tangent line at x equals 0. I have a horizontal tangent line at x equals 3. What happens in between those points? Well, the derivative is positive everywhere between those points, which means that function f has to be increasing everywhere. So if I were to draw a tangent line anywhere on this curve that I've graphed so far, it's going to be going upward until it gets to x equals 3, where it has to flatten out again. What happens if I keep going further right? If I keep going further right, then I have f prime takes on negative values. What does it mean if your derivative is negative? That means your function is decreasing. And it looks like from the graph, it is decreasing at a decreasing rate. So I think it's going to be something like that. All right. So I think we have a good idea what's going on from the y-axis to the right. Now what's happening, as we come from the far left and approach the y-axis. So let's look at our two values where the derivative equals 0 again. What's happening between x equals -3 and x equals 0? The derivative is negative everywhere between those 2 points. So what does that mean the function has to be doing between those points? It has to be decreasing. So if the function is decreasing from right to left, I believe it's going to look like this. Basically, I think I'm going to have symmetry over the y-axis here. So a couple things that I want to point out. First, since the derivative is negative, just to reiterate this, since the derivative is negative between x equals -3 and x equals 0, that means my function f has to be decreasing from x equals -3 to x equals 0. So anywhere I would draw a tangent line between x equals -3 and x equals 0, that is going to be, those are going to be negatively sloped downward tangent lines. All right, the last part of this graph I want to deal with is what's happening between, or what's happening to the far left of x equals -3. Well, my derivative is positive, so I think that means my function has to be increasing. So I think I can justify this is going to be symmetrical over the y-axis. So like I said, I'm not looking at the multiple choices here. So I'm sure there's a graph that has this shape. It might be vertically shifted upward or downward. But when we're told the derivative, we can't really, if we're told about the rates of change, we can get a lot of information about the behavior of the parent function f from there, but what we can't talk about is locations. We don't really know any y values that are on the original function. All right, moving on to 5. So we have some pieces of data here. So where x equals 1, we know something about the value of the function, the value of the first derivative of the function, and the value of the second derivative. So let's draw a partial graph here to kind of illustrate what's going on. So I really only know what's happening at one point, whereas that x equals 1. When x equals 1, y is equal to 2. So I know this point is on this function. F prime of 1 equals 0. What does that mean? So the instantaneous rate of change at that point is 0. So I'm going to have a horizontal tangent line at that point. So it's going to flatten out there, but I don't know how. So that's what the second derivative tells me. So the instantaneous rate of change of f is a positive value. So basically, as I come from the left of x equals 1, the derivative is going to be increasing, and then the derivative is going to become 0, and the derivative is going to be increasing thereafter. So because of that, I believe I have a graph that looks like this. It's gonna basically, as I go from left to right, I have negative slopes, a 0 slope, positive slopes. I have a concave up graph, and that's really what a positive second derivative tells you. A positive second derivative and a function that is concave up. Those are equivalent ideas. So does that help us answer the question? There's a relative minimum at x equals 1. That sounds plausible, but let's keep on looking. There's a relative maximum at x equals 1. I don't think that's possible because the concavity wouldn't make any sense. There is an inflection point at x equals 1. That's impossible because inflection points happen where the concavity changes. If the concavity is 4 at this point, it can't be changing. It has to be either 0 or it has to not exist. Not enough information is provided. I think I know everything I need to know. I know the value of the function and its first and second derivatives here, so I can say for sure I have a minimum at this point. And finally, no, there's 8 questions here. So let G represent the amount of gallons of water in a pool measured in hours since midnight. So I'm given the G of 12 equals 12,000. So let's just kind of take these one at a time, and then we'll look at the choices. G of 12 equals 12,000. So what does our independent variable T represent? That represents hours since midnight. So 12 hours since midnight, that tells me I'm looking at something that's happening at noon, at 12 p.m. And what does the 12,000 represent? The 12,000 represents the number of gallons of water in a pool. Okay, so let's just start writing stuff down. At noon, there are 12,000 gallons of water in the pool. Haven't even finished reading the sentence yet, but let's keep going. G prime of 12 equals -10. So based on what G tells us, what does G prime tell us? G prime tells us the instantaneous rate of change of G of t with respect to t. So it's the instantaneous rate of change of the amount of gallons of water in the pool with respect to the number of hours since midnight. So let's erase this period here. At noon, there are 12,000 gallons of water in the pool. And what? The volume is decreasing by 10 gallons per hour. Okay, so now let's look at the choices and see what fit. First, at 12 p.m., the number of gallons in the pool is decreasing at a rate of 10 gallons per hour. That sounds an awful lot, like what I wrote down. Next, at 12 p.m., there are 11,990 gallons of water in the pool. No, that directly contradicts this piece of data here. I'm telling you there are 12,000 gallons, not that there are 10 less. All right, next, we have a calculation here. What is this calculation doing? It looks like it's making a comparison between what happens at 14 hours past midnight, so 2 p.m. That's not what a derivative tells you. The derivative tells you instantaneous rate of change. And this calculation here looks like it's giving me a 2-hour time interval. That doesn't fit. The most number of gallons of water in the pool occurs at 12 p.m. That's probably not true, because if we believe this decrease here, then yes, as time continues, like at 12:01 p.m., there's going to be less than 12,000 gallons in the pool. That's probably true based on this rate of change. But what about what happens at 11:59 a.m.? There's probably going to be more than 12,000 gallons of water in the pool, because I have a decrease. So if I look backwards in time, I'm probably going to have more water in the pool. So I don't like this one either. So I think our suspicion was good that, the thing we wrote down was very close to this answer. We're going to accept that one. All right, finally, I keep saying finally, there are 8 questions, second to last one. So Stephen and his wife go for a long bike ride. This graph represents their distance from home as a function of hours. So based on the graph, what must be true? Let's see. So let's look at this choice by choice and see which ones fit. Stephen and his wife's acceleration was 0 at 2 times during the ride. What is going to tell me if my acceleration was 0? So this is a distance graph. How are distance and acceleration related to each other? Mathematically. Acceleration, we're calling this d of t for distance. Let's write out a string of things here. I believe that velocity, or speed in this case, is the first derivative of distance. I believe that acceleration is, I'll write this a couple ways, the first derivative of velocity, which in turn is the second derivative of distance. So how do I have a graph of d, of distance with respect to time. What on the graph gives me clues about the second derivative? That's going to come from the concavity. So what I'm going to look for is, I have to move back one more step. I'm looking for points where the acceleration is 0, or equivalently, the second derivative equals 0. So those are probably going to be inflection points. So really, let's look for inflection points here, those places where the concavity might be changing. It looks like in the center of the graph here, I have concave down. What about what's happening? So is it concave down everywhere? I don't believe so. It looks like, on the left and the right of this graph, it looks like I transition from being concave up. to concave down. So that one actually feels plausible. So it looks like I have two inflection points. This might be true. Moving on, the distance they traveled over 2 hours was 15 miles. I don't think that can be true because if this graph shows my distance from home, 1 hour away, I'm 50. So after an hour, I'm 15 miles from home. And then in another hour, I'm 0 miles from home. So I think at a minimum, I traveled 30 miles. So I don't think that one can fit. They were riding fastest at 1 hour. What do we think about that? So where's my maximum velocity going to happen? So where is velocity going to be maximum? I believe that's going to have to happen where the derivative of velocity is 0. So that's how we look. That's one thing we associate with finding max and minimum points is where the derivative of the function is equal to 0. So what is the derivative of velocity? That's the same as the acceleration being 0. Does it make sense for the acceleration to be 0 after 1 hour? I don't think so, because I think we said the acceleration was going to be 0 at these 2 points, which looks like a half and 3 halves. So I'm going to disregard this one. Stephen and his wife were accelerating from 0 hours to 1 hour. Again, I think for the same reason we can't say that's true, because it looks like I have positive acceleration for the first half hour, but then for the 30 minutes after that, I have negative acceleration because it's concave down. So I think, again, we're going to go with A. Now I'll say finally, final question here for this part. Which graph represents this situation most accurately? So what do these graphs show? These graphs show the distance between a neighborhood cat and my daughter Katie over 10 seconds. Let me get this out of the way of some of the graphs. So let's just take these 3 steps and see, if I can start eliminating some of these things. The cat approaches Katie from 12 feet away, so moving faster over the first 5 seconds. So she starts from 12 feet away. Do all these graphs start from 12 feet? They all do. Moving faster over the first 5 seconds. So the cat's moving toward Katie and accelerating toward her, which means the distance needs to be decreasing at a decreasing rate. As she's moving faster toward, so the distance is going to be decreasing at a decreasing rate. Does A fit with that? I think so. Does B fit with that? No, B looks like the cat is, initially moving rapidly toward Katie and then slowing down on the approach. So I'm going to throw out B. What about C? I have a straight line here. That's a constant. That tells me that's a constant velocity or a constant speed. I don't think that fits. And then D, I think D could be good as well. So now we're down to 50-50. All right. So that was over the first. Moving faster over the first 5 seconds. Okay, good. When the cat gets 2 feet away, it circles Katie. So when the cat is 2 feet away, it's going to walk a circle around Katie. What does that do for the distance away from Katie? Well, if it's a circle, that distance is going to remain constant. So because of that, I think A makes sense, but I don't believe D works anymore. Because what's happening around from 5 seconds onward, the distance is, in constant transition here. That can't be true if the cat's just walking in a circle. So without even looking at the third clue, actually, let's make sure it makes sense. The cat then quickly goes to lick Katie. The distance rapidly goes from 2 to 0. So I think A is the only one that encapsulates all of those criteria. All right, so that's part 2. Moving on to section or part 3. Use the graph to identify all x values such that the function is not continuous. Let's remind ourselves of the conditions for continuity. So f is continuous at x equals a if what? F of a exists. Let's just start there. Are there any points on this graph that are not in the domain of this function? It looks like, so let's just make a list here. X equals 0. Looks like when an x equals 0, there is no value. There is no corresponding y value. All right, so f of a exists. The limit as x approaches a of f of x exists. So let's negate that. Where on here might the limit not exist? So the limit's not going to exist, where we have a jump, right? So I believe that's also true of -8. Why do I say that? Well, because as x approaches, let's just write this down. The limit as x approaches -8 from the left of f of x is what? Looks like that's about say -1. What's the limit as x approaches -8 from the right? That is clearly not -1. That's about, we'll say -3. So those one-sided limits don't agree, which means the limit in general, the two-sided limit, can't exist. Is that true of anywhere else on here? I don't believe it is. So what's our third condition? The limit as x approaches a of f of x is equal to f of a. And like I've said before, this third condition basically encapsulates the first two. So basically, are there places where the limit exists, the function is defined there, and those two things don't agree? I think based on that, I have to include x equals 3. Because at x equals 3, the limit from the left and from the right is clearly a negative number, but the function is defined at what's clearly a positive number. So I think these are the 3 values where x is, or where f is not continuous. The next part, same graph, right? Yep, same graph, but where is this function not differentiable? So here's one thing we know. If a function is not continuous at a point, it cannot be differentiable there. So we get 3 points for free. So -8, 0, 3. So that's because the function is not continuous at those points. But the conditions for differentiability there, this is a stronger condition, which means it's possible for a function to be continuous, but not differentiable. So where does a function fail to be differentiable? Well, the one place it fails to be differentiable is where hard corners or like these cusps exist, because I can't think of a unique tangent line to generate there. So I believe I have to include -4. By the same token, I think I have to include 2, because there's a hard corner here too. Anything else to look at? I think that should be it. Where else will this derivative not exist? So before I go too much further, let's talk about what does it mean for a function to be differentiable? Well, one way to say it, which is not super limiting, but a function is differentiable if its derivative exists. But what is the derivative? The derivative is a limit, a very specific limit. The limit as h approaches 0 of f of x plus h minus f of x over h. I need this limit to exist. So it's not going to exist where there are hard corners because the limit might not be unique. So that's a problem. Um, it's also not going to exist if it goes to infinity. What would cause it to go to infinity? Well, that's going to come from if I have like vertical tangents. So where am I going to have vertical tangents? I believe I see one. Actually, I don't know if I can say that what's happening on the far left of this graph, but I feel a lot better about saying that that's happening here. So what is that value? I don't know. Negative 0.4, maybe. Do I see any other places where there are vertical tangents? I think I am intending to see one here. So what's that? Negative 6.5. So again, I think that's a complete list now. And these might be different. I know you were given like specific numbers to choose from. Mine might be a little off because I'm not looking at the choices, but they should be close. That should be a complete list there. All right, finally, question 3. I keep saying finally to questions that are not the last question, just ignoring that part of what I'm doing. All right, I want to rank the order greatest to least. So I have 5 points to categorize here. One thing that I was surprised by is that, and I think it's a little weird that 4 of these points are lettered, and one of them is just x equals 1. But yeah, I want you to include in your ranking x equals 1. So part A here is from greatest to least, rank the order of f of x. So f of x, not derivative, just f of x. That basically I'm ranking this in terms of y values. So basically, the largest f of x value is going to be the highest point, and then on down to the lowest point. So my highest point is point D, followed by C, followed by 1, followed by B, followed by A. So this function, as you read it from A to like from x equals A to x equals D, it's an increasing function. So the greatest value is going to be the furthest right, and the least value is going to be the furthest left, and everything's going to kind of stack up in that order. Part B, now I want to rank the derivative from greatest to least. I think an easier way to start this one is to talk about what's the least. So let's draw some tangent lines. So tangent line at A, tangent line at B, at 1, at C, and at D. I think it's easiest to talk about what's the least because 4 of these are positive and 1 of these is a horizontal tangent line. So the least is going to be A. That has a horizontal tangent line as a slope of 0. What's going to have so the rest are positive. So which one's going to be the most shallow? Like it's positive, but it's the least significant. I believe that's going to be D. What's going to be the next? I believe that's going to be C. And then 1. And then the most significant slope here, the most positive slope is going to be B. So from greatest to least, I believe I have B1 CDA. All right, question 4. Gotta move my speaker view again. This one was tricky because I think many of you probably looked at the graph and said, all right, that's f of x, and answered the question accordingly. This graph is not of f of x. This graph is of the derivative of f. It is of f prime. So that's going to change a lot about how this is answered. So part A, for what x values is the first derivative of x equal to 0? Since this graph is the first derivative of f, the places where it's equal to 0 is where it crosses the x-axis. That happens exactly at 2 points. Looks like 2 and 4. Part B is not worded the same, but the answers are very closely related to your answers for it. So for what x values is the first derivative of x positive? Again, we are looking at the first derivative. So where is this thing positive? It's positive between the two places where it's 0. So the interval I would give you is, I'm going to say it's an open interval from 2 to 4. Because the reason I'm not saying it's a closed interval is because I already told you that, or I'm already answering that at x equals 2, the derivative is positive. All right. Moving on. So for what values is the second derivative of f equal to 0? So the second derivative of f, that's f double prime. I am looking at a graph of f single prime. How is f double prime related to f single prime? Well, the second derivative, f double prime, is the first derivative of f prime. So I want to know where this function has positive slopes. So or in other words, where is this function increasing? And it looks like it's increasing everywhere from the far left of the graph to wherever this maximum is. So I'm going to say from 0 to, oh no, where's it equal to 0? I was getting ahead of myself. I'm going to say exactly at one place. I'm going to say x equals 3.1. Many of you said x equals 3. I was happy with that. Anywhere near 3 is good. And how do I arrive at my answer? I think I kind of, I'll go again, but I think I explained it a bit. We are looking at a graph of f prime, which means the second derivative of f is going to be the first derivative of the function depicted by this graph. So where does my function neither increase, or sorry, where does the function graphed here neither increase nor decrease? That's going to be where it's a maximum or a minimum. I don't have any minimum points. I do have a single maximum, and that looks like it happens at x equals 3.1. And then next, for what x values is the second derivative positive? So the second derivative of f is going to be the same as the first derivative of f prime. So I want to know where the first derivative of this graph is positive, and that's going to be where this graph is increasing. And I think that happens everywhere from the far left of this graph up to that maximum. So that's going to be a closed interval or open interval from 0 to 3.1. That could actually include 0. Looks like it's increasing at 0, or positive at 0. But yeah, I've noticed that many of you answered this question as if this is the graph of f, and that's going to throw your answers off quite a lot. All right, finally, part 4. I don't want to say I was lenient on this question because I don't think I was lenient, but there were lots of different answers that I found acceptable. These questions are very intentionally, open-ended, and they kind of have to be. If I ask you about the derivative, I'm not looking for like a canned answer that you can parrot. I'm not looking for a slogan. I want you to explain to me what a derivative is without kind of defining it in a circular way by somehow including the word derivative in your answer. So I'll try to give a few explanations here. So what does the expression below tell us about a function? The way that we've tried to relate it to you is it's a rate of change. And it's not a coincidence at all. This expression here is in many ways identical, or at least derived from the slope calculation. I want to know, speaking in general terms here, I want to know what the change in my y values is. So that's what the f of x plus h minus f of x is. And I want to know what the corresponding change in my x values is. That's what's signified by h. So that right there, that gives me an average rate of change. If I incorporate the limit, then that's where I'm trying to make h, the distance, the horizontal distance between x values, the vertical distance between x values. I'm trying to make that distance as small as possible, like arbitrarily close to 0. That's what the derivative is the the metaphorical bridge or metaphorical gap that I am bridging by taking my average rate of change over an interval of some size um, to my instantaneous rate of change over an interval of no size or an infinitely small size. So again, a lot of you got full credit on this without saying anything that was close to what I said. There's lots of ways to explain this. Part B, explain this idea of this expression and how it works. As if you were to explain this to somebody, basically think about explaining it to your pre-calculus self. How would you explain this to somebody who doesn't know what a limit is in this context? And like I said, that's basically the limit is I hesitate to say only big idea, but you've learned a lot of new things in this class, and all of them are informed directly by a limit. The limit is like the big, the most valuable new concept you talked about. But what is this expression? Basically, how does it work? I think the way I would explain it to a pre-calculus student is I would lean heavily into the idea of a slope, because that is something that pre-calculus students have been calculating for years now. And basically, I want to know what that slope looks like as kind of like I pinch closer and closer, those x values of each other. And I feel like I'm just kind of explaining what I did for A. So, many of you, your answers for A and B were kind of like linked, and that's fine with me. But basically, how does expression work? Basically, you're finding your rise over run or your slope or any of the other ideas you like associate with this average rate of change. You're finding these over smaller and smaller and smaller windows, and hopefully when you do that, you get a sense of what that slope would be if your window totally disappeared. That's really what this expression does. All right, question 2, talking about the suns over the last or this period of 4 seasons. For what period of time is the first derivative negative? So if our function, do we name this thing? Let's call it F. Yeah, let's call it wins. WT. W of T represents number of suns wins in the how do I want to simplify this? In the season beginning in year T. Okay, so where's the first derivative negative? So if this is my function W, then what does the function W prime represent? W prime is going to represent the change, basically the change in wins. We can't really say instantaneous, because all we're looking at is like year to year, but we're kind of taking some liberties here. So if we're looking at changes, let's get a value of W prime between these seasons. Between these first 2 seasons, what's the change there? I think it's an increase. We won 17 more games. How about between these 2 seasons? I think that's an increase of 13. And then between these 2 seasons, that is unfortunately a decrease of 19 wins. So where is the first derivative negative? I think the only place, in this sample here where the derivative is negative is, there are lots of ways to say it, but really over 2022. So in the space between, or in the time between the 2021, 2022 and 2022, 2023 seasons, that's the only place where the first derivative is negative. All right, part B, for what period of time is the second derivative negative? What does the second derivative tell you? The second derivative tells you the rate of change of the rate of change. So now what I want to do is this. What's happening between these rates of change? Well, between the first two seasons, I've won 17 games. And between the second and third, or sorry, between the first two seasons, I increased my win total of 17 wins. Then the space between the second and third seasons, I increased my win total by 13. So what about now? How do I compare those two, like, spaces between seasons? Well, from one to the other, I lost like my win total. Not so. Another way to say this: the rate of increase of my win total decreased by 4. So I'm winning more games, but the increase in those wins is diminishing. What about between the third season and the fourth season? What happened to that rate? That plummeted. So up 13, sorry, an increase of 13 compared to a decrease of 19. I think that's like the second order decrease of 32. So for what period of time is the second derivative negative? I think basically everywhere, everywhere you can measure it. So from 2020 onward, you have this, like, regardless of whether the first derivative is positive or negative, it is decreasing. So the second derivative is negative everywhere. Ooh. And finally, question 3. This is another one that I again, it's not that I was lenient, but I gave full credit or close to full credit for a lot of different answers because there's a lot of different ways to answer this question. So explain how you would graph this derivative function. So I've given you a graph of function f with respect to x. Verbally explain to me how you'd graph the derivative. Again, lots of ways to go about this. Some of you kind of gave me like this, recipe from left to right, very like kind of like you were drawing me a map. Like, all right, start at this point, and then gradually increase to this point, and then decrease to this point. Like that all works fine. I think I've done this method before, but I think it's something I think works for me, and I suspect a lot of you as well, is a good place to kind of get your bearings is to think about where this graph has a derivative value of 0. That's going to happen at a maximum or a minimum. So I believe I would start by saying, all right, f prime is going to be 0 at exactly 2 points. And that's going to be at x equals negative 2.3, kind of estimating, and positive. Yeah, let's make this really, let's be more aggressive with our rounding. Let's say, all right, this function, the derivative is going to be 0, equal to 0 at x equals negative 2.5, and also x equals positive 3. So we can start there. Then from there, what happens in between those points? Well, between those 2 points, the derivative is everywhere negative, because anywhere I were to draw a tangent line, those would be negatively sloped. So it's definitely going to be negative, but can we give some kind of detail as to how negative? So let me erase my tangent lines. Where do I think the most significant negative is going to be? It looks like it's going to be right about, across on the y-axis. So I think I would then say that I'm going to have, in this window between x equals negative 2.5 and x equals 3, I'm going to have the least value of my derivative happen at x equals 0. And I'm going to estimate that's about negative 1/2. I don't think it's quite negative 1. So I would think my derivative is going to have, basically, let's kind of put this all together. At x equals negative 2.5, my derivative is going to be 0. Then it's going to decrease to a minimum at x equals 0, where the derivative is going to be equal to about -1/2. And then it's going to smoothly increase back to 0 at about x equals 3. So I think that hopefully that's sufficient to describe what's happening between these two places where the derivative is equal to 0. Now let's think about what happens to the right. So to the right of x equals 3, I believe I could say that my derivative is going to be increasing and increasing at a positive rate. So you should draw a graph that increases, but and is also getting steeper. Last kind of loose end here is what happens to the left of x equals -2.5. The last thing I would say here is that everywhere to the left of x equals -2.5, I have a derivative that is positive. So it's going to increase to a 0. So the derivative needs to be negative, and it looks like it's at the far left. So at x equals what? 1, 2, 5, 6. At x equals -6, the derivative is going to be about, I don't know, 3. So the point -6, 3 should be on the graph of my derivative, and then it should increase to 0 at about x equals -2.5. So I think I gave plenty of detail there, but there's a lot of ways to describe what's going on with that graph and how to sketch the derivative from it.